This lesson really gets into the particulars of the binomial distribution, and I have mentioned it a couple of times in past lessons. These four things are what makes a probability distribution binomial. There has to be a fixed number of trials, and a trial is any single observation or outcome, like when you roll one die. So you have to know how many times you're going to roll the die. Or if you're going to ask people questions in a survey, you have to know how many people you asked. There has to be a fixed number of trials. Each one of those trials must be independent. One outcome has absolutely no effect on the other outcome. And then every trial has to go into two categories, this being the binomial part of it. The two categories is either it did or it didn't happen. It's success or failure. And success could be something negative in here if what you're looking for is a negative response. So if you were looking for the number of people that are going to say no, you can count no as a success. So don't worry about it that it's positive or negative, and that's what that little reminder is over here. Success is simply whatever it is you happen to be looking for. And the probability of success remains the same in all the trials. So you could have a binomial distribution then if you say you're going to roll a die 4 times and you're trying to get a 3. Well, then the fixed number of trials would be 4. Every roll is independent. It has no outcome on the other one. You'll either get the 4 or you won't. Now, I know that there are other outcomes out there, but you can say you got it or you didn't. So you don't worry about the fact that you could roll a 1 or a 6. You just say I got a 4 or I didn't. So that's success or failure. And then that probability of you rolling the 4 would stay the same in all the trials. So these are the things that make something binomial. Now, our lettering that we're going to use for this, N is the number of trials. So in my previous example, it's you're going to roll the die 3 times or whatever. And then X is the specific number of successes. So it's how many times that's going to happen. And then P is your probability of success. And generally we're going to use that as a decimal. It is sometimes a fraction though. So like rolling a 4 might be a 1 out of 6 or 1/6. And then if you had a decimal, that would be the equivalent of it. Q is the probability of failure. So a lot of times you can just find Q by doing 1 minus P. If they tell you the probability of something happening is 25%, then the probability of it not happening is 75%. So we can just subtract there. P of X is the probability of getting exactly X successes from N trials. When an adult is randomly selected with replacement, there's an 85% probability that this person knows what Twitter is. And this is based on results from a Pew Research Center survey. Suppose we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. These are the things that you have to look at. Is there a fixed number of trials? Yes, there is. How many trials were there? 5. We're going to stop 5 people. Are they independent trials? In that one outcome has absolutely nothing to do with the other one. Yes, one person knowing what Twitter is will have nothing to do with the next person knowing what Twitter is. Are there 2 outcomes that we can define as success and failure? Yes. Since we are looking to see if they know, then knowing would be success. And again, if you wanted to say what is the probability that they don't know, then don't know would be success. It's just whatever you're looking for. Does the probability of having a success remain the same every single time? Yes, it said that there's an 85% chance that a person knows what Twitter is, and that is not going to change ever. So the probability that they know what Twitter is going to be 0.85. And by the way, that indicates that the probability they don't know what it is 0.15. So this one is going to fit a binomial distribution. Now, this is the exact same thing. It's just kind of written out differently because you may have homework that fits it like this. So we're just going to kind of rewrite it on here. N is 5. X is 3. Now, where did that come from? Because it's right here, 3 of 5. This is my number of trials, and this is the number of successes I'm looking for. P is the 85%. I put that on the previous slide. Q is always the equivalent of 1 minus P because they're complements. And if you knew Q, you could find P by doing 1 minus Q. But that's where I got the 0.15. Okay? Now, we're going to talk about how to calculate this in a minute, but here's just something to keep in mind. It's called the Guideline for Cumbersome Calculations. Because one of our requirements is that all of these results are independent, then sometimes if you have a large population, it just gets really hard to keep calculating it. So what happens is if your sample size is no more than 5% of the population, you can treat it as independent, and it doesn't matter if they are or aren't. It's such a small thing, you can treat that as independent. And sometimes your homework is just going to ask you, can we treat this as independent? So now let's look at how to apply some of this. The easiest thing you can do, there's several methods for finding a binomial probability. One of them is based on a formula. One of them is with technology, which is what I'm going to show you. And then the third one is from a chart. And if you don't have this TI-84 Plus, you might can find a binomial probability calculator online somewhere else. And certainly you can look in your online textbook for how to apply the formula or use a chart. But this is that same problem over here, okay? So in order to work it on your calculator, you're going to go to Second, VARS, and then we'll choose the binomial PDF. Now the reason it's PDF is because we are looking for a particular outcome, just the value of 3. And you'll see the contrast between that and the CDF, which I know you'll see on your calculator also in just a minute. So again, just to show you on here, if I want to bring that up, I'm going to go to Second VARS, which really means I'm trying to find my distribution, which is binomial. And you can go up or down. You see you have 2 binomial ones, so look very closely at these. And I'm going to go with P because this is a particular value. So I want the binomial PDF. Okay? And so when I hit enter there, then I get to the screen where I can enter things about my trials. So we said there were 5 trials because we're going to stop 5 people. The probability that they do know what Twitter is 85% or 0.85. And I'm looking for the probability that exactly 3 of them know. And that is my P, or my particular value. Okay, paste and enter. And I get this decimal, which is exactly what's on the screen there. It's just a lot smaller print. So that probability is approximately 0.138. And generally on probability, we round to 3 decimal places, but always make sure that you read your instructions carefully. So 0.138. Second VARS binomial PDF. Okay, this is exactly 3, right? This one says fewer than 3. So let me talk about that for just a minute. When you do a binomial CDF, what you have to think about is your number of successes. And think about that from least to greatest. Okay, so it's going to start at 0 successes, 1 success, 2 success, 3 successes, all the way up to n successes, all of them. The calculator is programmed to add these successes from the left. So fewer than 3, if I want fewer than 3 successes, then what I'm really wanting is the probability of 0, 1, or 2. Since the calculator is programmed to add from the left, it is going to stop at the value you give it. So this is relatively small here, but that's why there is a 2 listed as my x value. So I'll bring the calculator back over and we'll make it a little bit bigger for you to see. But I'm going to make another case of that. It's adding from the left all the time. But it's very important that you remember that. So when we bring our calculator over, we're going to get a second VAR's binomial CDF. Okay? So second VAR's, you can go up or down. It doesn't really make too much difference. But I'm going to stop at the CDF this time. The C stands for cumulative. Cumulative means that you're adding them up, okay? P was for a particular value. C is a cumulative, okay? So I'm going to choose the one with the CDF. Once again, I can say we have 5 people. The probability of success is 0.85 or 0.85, but fewer than 3. So fewer than 3 means that I really want it to add up to 2. So putting a 2 here means it will add from 0, 1, and 2 successes. And you've got to keep in mind then it's going to add starting at your lowest number of successes, 0, up to the value that you put there. So this is going to add through my first 2 successes, so 0, 1, and 2. And I get the result of 0.027 approximately. Let's take that and say, suppose I don't want this section on the left, I'm wanting the section on the right. That is the subtle difference between this problem and this one. This one says more than 3. So if I look at this again and I have 0, 1, 2, 3, 4, whatever, this is just going to keep going until we get to n. In this case, 5 would be our n, so it would just be 0, 1, 2, 3, or 5. And one more time, what is this referring to? The number of successes. My calculator is programmed to add from the left, but what I want this time is more than 3. More than 3 means I want these. So what I'm going to have the calculator do for me is add up the ones I don't want, and then I will do 1 minus the ones I don't want. So 1 minus the probabilities with 0, 1, 2, and 3 might be one way to say that. But in order to do that, the calculator will add these up for me if I use this CDF. Since I don't want the ones on the left, I'm wanting the ones on the right, I will do 1 minus that value. So it is there, so I just feel like that's a little bit small for you guys to see. So we'll come back over here and I'll say, well, I don't want, if I want more than 3, then I don't want up through 3. So what I'm going to do is, first of all, make it calculate that for me. So I'm going to my CDF, and I'm going to tell it, you notice it keeps the numbers that I had in here before, but I'm going to tell it, please go ahead and add up through 3. I guess you have to tell your calculator, please. But if I add up through 3 and I get an answer, that's the part I don't want. But since all probabilities add to 1, I can do 1 minus that answer, and I get the probability of 0.835. Okay. And this little picture here is entirely wrong. What I did is correct. Let me bring that back over there. What's on that picture is wrong, because see up here where it says CDF, and if you look at this though, that's a PDF, so that's an incorrect thing. That part's wrong. That part's wrong. Shame, shame, shame. Okay, you want the CDF. And we're going to do 1 minus the CDF. So bringing that calculator back up again, this one is correct. We've got the CDF, and then we have 1 minus that answer. Okay, CDF is cumulative. I had it add up the first 0, 1, 2, and 3, and then I subtracted that off. Now, taking us back to our previous one, then when you actually do want the first part, 0, 1, and 2, I just use the binomial CDF. This picture's correct. Okay, so let's look at another example. Based on the Harris poll, 60% of adults believe in the devil. Assuming we randomly select 5 adults, find the following. Find the probability that exactly 3 of the 5 adults believe in the devil. 3 of the 5. So what you're going to need to know when you go to your binomial PDF, the reason it's a PDF is because it's particular. Exactly 3. And it's going to ask you the number of trials. It's going to ask you for the probability of success. So what is success this time? The believe, and that is 60% then that believe. And then it's going to ask you for X. What is the particular value that you're trying to find? And that is 3. So I'm sorry that the P from the PDF and the P over here that you enter are not the same, but this one is your probability, and this P is for a particular value. Now I'll bring that up in just a minute and look at that. But here, the probability that the number of adults who believe in the devil is at least 2. Well, what you have to do again is, whether or not you're writing it down, you're just going to think 1, 0, 1, 2, 3, 4, 5. These are all the possible outcomes, right? But if we want at least 2, at least 2 means 2 or more. So these are the ones you want, and they're on the right. So to do that, what you actually have to do is use 1 minus, because it is going to add up the values on the left, okay? So let's get our calculator and do those again just so you can see. Probability is exactly 3. You get to this under your distribution, so second bars. You can go up or down. I think it's slightly shorter, but no big deal to go up. Since it's exactly 3, that's a particular value. I choose the PDF. I'm going to ask 5 adults. The probability that they believe in the devil is 60%. And I'm looking for exactly 3. So my answer is approximately 0.346. 0.346. What about the probability that at least 2? Well, you can do just the CDF, but you can go ahead and then do 1 minus that answer. That's what I did before. Or you can do 1 minus, because I know I want the complement. I want the other part. The other part of a cumulative, because I wanted to add it up. 5 trials, 60% chance that they do believe, and at least 2 means I don't want 0, 1, or 0 or 1, and you can see that again down here. I am trying to do at least 2, so I've got to subtract off the cumulative probability through 1. So when I put that 1 there, but it's on a C, it's going to add up the probability of 0 and the probability of 1. And then I am subtracting that, 1 minus, so it's the complement of it. And I get 0.913, 0.913. Cumulative, the C one adds, and it always adds from the left, and the P one does a particular value. this is kind of that summary. If you want a PDF or a CDF, which one? If you want a particular value, you're going to use a PDF, and that is going to be x equals a particular number. Because a CDF normally starts at the sum of 0 and it goes through whatever value you enter, okay, that one is going to be what you're using when you're wanting less thans. Okay, so if it says less than, you've got to think about what you're wanting there. And if you need the complement, you have to do 1 minus. Suppose it says less than or equal to or greater than or equal to. You have to rephrase that. So you just kind of have to think less than 3 means that you need to do 0, 1, or 2, so you would have to use a 2 here. But if it says less than or equal to 3, that means you're doing less than 4. Okay, so you can just kind of rethink that through, and I encourage students a lot of times just write out those numbers 0, 1, 2, 3, 4 all the way up, and just, you know, kind of like I was doing. So it even makes it more sense going down. N times P is mu. Then you take the N times P times Q and you'll get your variance. Then take the square root and you get your standard deviation. So you're going to find your variance and then your standard deviation. And you do need those formulas. Okay, so let's apply that. Here we've got a lot of words. That's the word problem. If there are 460 overtime wins in NFL football games, and the probability of winning is 50%, the probability of losing is 50%, if we assume that by winning the overtime coin toss, there's no advantage. So both teams have the same 50% chance of winning the game in overtime. Now I realize this is just based on, this is just an example. Please don't get hung up on the quarterbacks and the skills level and the kickoff and stuff. This is just saying they're going to win or lose. Find the mean and the standard deviation for the number of wins in the groups of 460 games. Well, we know that the mean is equal to N times P. The number of games we have here is 460, and that probability would be 0.5. Okay, so that should be 230. Now, if I want to find the standard deviation is the square root of N times P times Q. So that's going to be the square root of 460 times 0.5 times 0.5. So 460 times 0.5 times 0.5, and then that's 115, and then the square root of 115 is approximately 10.72. I really should have just gone to 10.7, I think, on that one. So it does round to 10.72, but we didn't have any decimals over here. All right. Use the range rule of thumb to find the values separating the number of wins that are significantly low or significantly high. So that range rule of thumb is going to be when we take our mean plus or minus 2 standard deviations. So that means I've got 230 plus or minus 2 times 10.7. All right, so first of all, let's do the subtraction one just so that we get our low number first. So if I take 230 minus 2 times 10.7, I get 208.6. And then when I go back and I do the exact same problem with the plus, so 230 plus 2 times 10.7, I get 251.4. Now what these two numbers are is kind of the kind of the wall. Anything lower than 208.6 would be significantly low. Anything higher than 251.4 is significantly high. These are the two values that separate them, the low and the high. So is 252 overtime wins and 460 games significantly high? Well, 252 is bigger than my upper limit of 251.4. So yes, it is significantly high. Now, besides looking at the range rule of thumb, you can also just look at the probability of having that many or more successes. Now, do note that it's the or more. And if the probability of having that many or more, or that many or fewer successes, and in both cases you see is less than 5%, then we can use probability along the way there. So let's go back and consider that same game, and let's just consider how we would do that with probability. So backing up to our previous scenario, what it says is there are 460 wins, 252 of those had to do with people that are teams that had won the toss. Okay, so 252 overtime wins because they won the toss out of that 460 games. Okay, 252 out of 460. So what we would do if we were going to apply this is say, okay, is 252 successes among 460 trials would be significantly high if the probability of 252 or more successes is 0.05 or less. So if we wanted to find the probability that X was greater than or equal to 252 or more, then really what we can do is find 1 minus the probability that X is less than 252. The reason we want that less than has to do with that binomial again, because I know that when the calculator adds it up, it's going to add up the probability of 0, the probability of 1, the probability of 2, and it's just going to keep going. Somewhere out here I have 252, 253, and so on, all the way up until I get to that 460 games. So that's a long list of numbers, but the ones that it's going to add up for me come from the left, and I want it to add up everything in front of 252, which means I actually want it to stop adding at 251. So then I can use my calculator, and I'm going to bring it back up, and I can say, okay, let's do a binomial. I could have put the 1 minus in there first, but I didn't. But now this time I've got 460 games. If the probability is 0.5, and I want it to add, I know it's going to add because of the C, it's cumulative, and I want it to add up, I want it to add up everything in front of 252, so that's 251. And then 1 minus that answer. So the probability of getting 252 or more successes is 0.022. And then this is less than or equal to 0.05. So again, we would say yes, it is significantly high. Okay, so if the probability of that many or more or that many or fewer, if that is less than 5%, less than 0.05, then we are setting it off to say it's significantly high or significantly low. That's what I've put in here on this last screen so that you can see that. If we know what we've got is the result of 252, well, that means we want to subtract off the cumulative of 251. And so I just kind of put those pictures in there coming from the calculator so that you can see that again. And that takes care of this lesson. So just get in touch with me, ask the instructor, or email if you have questions.